All right, the very last topic that we're going to address when dealing with composition of functions is identifying any domain restrictions. Okay, and it turns out that when we identify domain restrictions of composed functions, there's sort of a multi-stage process going on. So the first thing that we want to do is we want to identify any domain restrictions off the inner function. So whatever function we're given, there's going to be an inner one and an outer one. We want to figure out, is there anything that can't work in the inner? Now that restriction I just want to write down somewhere. That's actually part of the answer. The question then becomes, is there any new restriction that gets brought up based on how the composition turns out? And so I want to form the new function. I want to form that composed function, f of g of x or g of f of x or whatever. And then I want to identify any restrictions off the new function. Then, once I've got, so I've got my restriction off the inner, I got my restriction off the new, I want to combine that together. So I want to write my domain statement in interval notation, and I want to include any restrictions from the inner function that we looked at earlier, and any new restrictions that we gained when we formed the composed function. All right, so let's look at some illustrations of this. We've got, here we're going to go both directions. I'm going to find g of f of g of x and g of f of x and their respective domains. Okay, so to find, first I want to start by identifying any restrictions. So looking at f, it's not a fraction, it's not a square root. So f is going to have all reals. And g is sort of the same thing. It's not a 2x minus 1, it's not a fraction or a square root. So we start off with two things that don't have any restrictions. And then I want to go ahead and form, and like I said, we're going to do this both directions. So f of g of x, g is on the, sorry, f's on the outside. So something squared plus 3, and I want to stick that 2x minus 1 and evaluate that at that. That would be 2x minus 1 times 2x minus 1 plus 3. So 4x squared minus 2x plus 1, and the plus 3. And so we get 4x squared minus 4x plus 4. Alright, so there's our composed function. Now, did we pick anything new up? Nope, it's still a polynomial. So the domain of f of g of x, we don't have any restrictions at any stage of this process. That's just going to be all reals. Okay. Now, you're typically going to see stuff like that with polynomials. All right, so now let's go the other direction, where I want g of f of x. Okay, so now f is on the outside. It's the outer function, so that's going to be 2 times something minus 1. And I want to place the g function inside that, so 2 as x squared plus 3. And then do any simplifying I can. So that's 2x squared plus 6 minus 1. And I can see like terms on the 6 and minus 1, so 2x squared plus 5. And then I want to look at that domain. And of course it doesn't pick up any new restrictions because it was just two polynomials. So my domain then for the total is negative infinity times infinity. So as you can see, this is kind of on the, I wouldn't say tedious side, but it's not that bad when you're forming two polynomials. Question is, what if they're more complicated? Okay, so now we're dealing with a quadratic and a square root. Let's start by identifying any individual domain restrictions off the two functions. So f is polynomial, no fraction, no radical on it, so it doesn't have, f does not have any restrictions. G on the other hand, okay, it's a square root. So if you recall, we would take the square root and identify what would make the inside piece greater than or equal to 0. And so that would be -1. So -1 out to infinity for the domain of G. Okay, so right now we're just going to keep track of that, put that off to the side. When I want to figure out what f of g of x looks like, and then see if I pick up any new restrictions from it. So g in this case is the inner, so f being the outer is going to be something squared minus 1, and replace that g in there. And if I square a square root, I end up getting rid of the symbol. So it's x plus 1 minus 1. And I can see the 1's cancel out, and I'm left with x. Okay, so interestingly enough, x is a polynomial, so there's no restriction on it. So the domain of f of g of x is going to be the restriction of the inner. We didn't pick up anything new, so it's got to be at least the ones that for g. Okay, let's go the other route, meaning let's switch directions and let's go g of f of x. Okay, this time f is on the inside, and so g's on the out. So it's the square root of something plus 1. And I'm going to put x in there, so x squared minus 1. And I can see that the minus 1 plus 1 cancel out, so we're left with square root of x squared. And of course the square root of x squared simplifies down to x. Okay, so that's our composed function. Now, interestingly enough, they're the same. There's sort of another reason for that, and that's another topic altogether, but there's sort of a connection between these two equations. But the domain is where it gets interesting, because the domain for g of f of x, well, let's see, f is the inner, f didn't have any restrictions. The composed doesn't have any restrictions. So the domain of that particular composed functions would be -infinity to infinity. All right, our very last example that we're going to address are these two rational functions. So yes, we're going to end with fractions. And to start off with, let's look at individually what can't they have in them. So the domain of f, now I know typically we do this in interval notation, but our goal is to do the composed function here. But so f, just looking at it, I can tell I can't have a -1 in that domain. And in g, I can't have a 3. Again, take the denominator, set it equal to 0, and solve. Okay. So now I want to do f of g of x first. Okay. G is on the inside, f is on the outside. Well, I have 1 over something plus 1. So what am I going to fill in that hole with? I'm going to fill it in with g. Now, if you just want to take a moment, gather your thoughts, yes, we have a fraction inside a fraction. It's perfectly fine. This is a skill we teach lots of students, so we can deal with this. Looking at our fraction, we want to come up with a common denominator that we can multiply everything by. And the only thing I can think of is x, well, not the only thing I can think of. I don't want to make it sound like we have options. If you look at the denominator, the only thing that's there for a denominator is x minus 3. So I'm going to multiply everything by x minus 3. Now, when I do that, up top I have 1 times x minus 3, and I have x over x minus 3 times x minus 3 plus 1 times x minus 3. Oops, sorry, I didn't mean to go that far there. Okay, so up top, in the numerator, I just have x minus 3, not too bad. The x minus 3 is in the denominator part, so that part cancels out, and I'm left with x plus another x minus 3. It's like we can't get rid of this thing. So what's left, we have x minus 3 over, looks like 2x minus 3. So we didn't have anything to distribute, so that's why the 3 stayed at 3. Alright, so that is our composed function. X minus 3 over 2x minus 3. Okay, now looking at it, does it have any restrictions? Well, it's still a fraction, and I want to identify where's that 2x minus 3 going to equal 0? Let's see, so we would add 3, so 2x equals 3, and then we would divide by 2, so we get x does not equal 3/2. Okay, so the domain of f of g of x, going to do the number line approach. So here's 3/2, it's got an open circle. And up top, we said earlier that since g was the inside, that I can't have 3. So come identify that, and then I want everything in between those two spots. So I've essentially broken the number line up into 3 regions. And so my composed domain is going to be negative infinity up till 3/2, union 3/2 up till 3, union 3 out to infinity. Okay. All right, let's reverse the order. Let's come back up here, and let's do g of f of x. And just kind of see how that compares. Okay, so this time f is the inside guy, and f we've identified cannot be -1 for its domain. G is the outside, so looking at that, that's going to be something on top minus something minus 3. Alright, so what am I going to fill in those blanks with? I'm going to fill them in with f, so 1 over x plus 1. Alright, now I need a common denominator so I can get rid of those fractions, and I can see that the only denominator I have to deal with is x plus 1. So I'm going to multiply x plus 1 over x plus 1. I didn't mean to have so many parentheses there. So what that's going to do, that's 1 over x plus 1 times the x plus 1 up top, and that's 1 over x plus 1 times x plus 1 minus 3 times x plus 1. And what do I notice? I notice that in the numerator the x plus 1's divide out, and I'm left with 1 over, and that divides out, so I'm left with 1 minus, and then I can distribute that in. So 3x minus 3. And if I combine like terms, I get negative 3x minus 2. And so that's my new function. So g of f of x is 1 over negative 3x minus 2. And then I want to identify if there's any new restrictions off that statement. So where is 3x minus 2 going to equal 0? Because that's not what I want. So I'm going to add 2. Kind of cover up that. So negative 3x doesn't equal 2. I'm going to divide that by negative 3. So negative 2/3. Okay, so let me try the number line approach. I know negative 2/3. I don't want, going way back up to the beginning, we said f was the inner, and f couldn't have a -1 in it, which turns out -1 is actually smaller than that. Okay, so there's my number line, and I still have broken it up into 3 regions. And so the domain, I guess I should identify that. the domain of g of f of x is negative infinity up to negative 1, negative 1 to negative 2/3, and negative 2/3 out to infinity. I think I snuck it in there. So yes, fractions do make this more complicated, but they're not that bad.